with the second session of the morning with Michele Doro. More fundamental physics, more other topics, everything else.
Yes. So I anticipate that I think the earlier lecture was already a lot of information, and now even more. I hope you can manage to stay focused, and okay, we'll try to do it together. The issue here is that I will try to cover more than one topic, and yeah, it's not that easy in 1.5 hours, but let's see, okay? So we are still trying to have a good lunch in 1.5 hours with Zwicky. Okay, so the topics I already anticipated. It will be for surely action-like particles, primordial black holes. If we have time, then magnetic monopole and an LIV, okay? If you work in any of these topics, let me know after that maybe I can give you some more material. Of course, as before, no, we have to look for tiny events in any of these cases, and we need extraordinary claims to make extraordinary evidence. This is part of the complexity of this, okay? Of this that we will talk about. All of these are again described except for LIV in this contribution here. If you're interested, just let me know. Okay, so let's start with action-like particle. I want to put some names of the colleagues that I work about, and for these topics, I want to show you that for all of this, I checked online the number of papers discussing the topic that we will talk about today, and you see that, okay, it's true that there is a general trend to fill archive with many papers, but you see how the interest in action-like particle really increased in the past year. So some of the topics are more into the mouth of everybody because of several reasons, and this is one of the hot topics now, even hotter than particle, dark matter, and the WIMPs that I told you before. So everybody is looking for action-like particle now. We are here, you remember this plot. We talk about the WIMPs, which is something around the GeV and TeV. And now we move to ultralight dark matter, who's one of the best candidates is the WIMP, the action-like particle, sorry, that we will see can leave imprints on our gamma ray spectra. Okay, so as with any dark matter problem or any new physics, you don't want to invent a new physics to, say, to justify your little problem. You have to be generic. So the birth of the axion was back in the 50s, I think, by Pechet and Quinn, which tried to solve one of the standard model problem, you know, that we have the matter-antimatter symmetry, for example, neutrino oscillation that are not written here, with dark matter, of course, as well as the strong CP problem, this not observed CP violation related to the strong force, okay? And as physicists do, okay, they invent a new particle, a new field, the theoretical physicist, the symmetry, which is spontaneously broken. And then there is a first candidate, the action, which is a model as a particle which has Fa is in the interaction strength and Ma is the mass, and they are kind of related one another. But then these models become found in many extensions of the standard model. So the action fixes the strong CP problem, and that was his birth. Being a new candidate particle with a sort of mass, it's also a candidate for dark matter. Now, I didn't go into that much detail here. This is very light, so I told you that dark matter is cold. But here we escaped that problem because this was is not yet another particle in thermal equilibrium in the early universe. So it doesn't follow that rule that to be cold must be in thermal equilibrium. So this is a non-thermal candidate of dark matter. We will not talk about the action, but what is called action-like particle, which is a general pseudo-Number-Goldstone boson, which comes from many theories. So it's not just the original version of it. And the difference between the two is, well, first, this doesn't actually solve the strong CP problem totally. But then this relation between mass and coupling is free now. So we can have, as we will see, different masses and different couplings for the action-like particle. Okay, so it's a new particle that I will show you the interaction in a few slides. Why the name? Okay, action actually exists, and it's a dishwashing soup in the US. And Pechet and Quinn invented the name because he was fixing all the problem. And you will see there are several theories about, several studies about action, and he fixes all problems of transparency of the universe, strong CP problem, whatever. Okay, so hence the name. So this is a scary plot again. Okay, I scare you a lot. This is what is called the parameter space of the action, like particle. On the x-axis, we have the mass, and you see that this kind of particle can have mass ranging from 10 to the minus 12 electron volt, very light, to 10 to the 7 electron volt, and this is the interval for the cross-section. Also, many, many orders of magnitude. We see, in general, that there is a bunch of people looking into the action-like particle. Generally speaking, the blue limits are cosmological, the red one are from lab, and the green one are from astrophysical observation. This line here, you see there is a direct relation between cross-section and mass, so this is axion candidates, and these are axion-like candidates. I will focus on this part. You see our names, Fermi, Markarian, this is where we will be working, so in a tiny space here. Okay, so there are a lot of exclusion, but still action can exist in any of these parameter space or not exist at all. What is, besides the particle, we want to see the interaction with photons. We are interested in photons. So there are two ways, generally speaking, in which you can have interaction. It's always a three-vertex problem. Okay, you have an action which can interact with two photons here, or so this is a decay, for example, action decaying photons. But the same interaction can be seen if you have an action interacting with the magnetic field, okay, and generating a photon, okay? And you can read the plot like this way. So if you have an action passing through a magnetic field, I will discuss this, can become a photon, and vice versa. If a photon passes through a magnetic field, can become an action, okay? There's no need of going into the Lagrangian. But as we are interested in most on this part here, we want to look at places in the universe where we have large magnetic field, large B's in the space. And if we know the Hillas plot, and we know that the largest magnetic field are found at very different scales, from the scale of neutron star, gamma ray burst, active galactic nuclei, active galaxies, galaxy cluster. Okay, so all of these targets are places in which there are strong magnetic fields. By strong, I mean order of micro Gauss, okay, or even here, or even larger. So at the end, for us, you take a gamma ray. If the gamma ray is traveling through magnetic fields in the universe, then there is a chance that there is a conversion of gamma rays to action-like particle. Okay? Let us see it in more details. Let's take, for example, an AGN. Okay? It's an active galaxy, and you have a jet. Okay? So these lines here are gamma rays. Okay? Now, between the source and the Earth, there are a lot of magnetic fields. Okay? There is the first one, which is the magnetic field within the jet, okay, which is of the order of Gauss. I think it's micro Gauss here, not Gauss. And coherence length of 1 parsec. So if a photon travels, gamma rays travel within the jet, it interacts with the magnetic fields. There is the magnetic field in the galaxy cluster. So if the galaxy is embedded into a galaxy cluster, in the core there is the possibility of having, again, micro-gauss magnetic fields with different coherence length. So second magnetic field. There is the intergalactic medium magnetic field. This is much smaller, below nano-Gauss. We will talk about that later, with larger coherent length. And finally, we have the magnetic field within our galaxy, okay? 1 micro-Gauss, and which is well known, okay? So during all these fields, what can happen is the following. You see, you have a photon interacting with a magnetic field, which can become an axion, okay? And then could be reconverted into a photon, for example, at the end of the passage. You can have conversion from axion to photon and from photon to axion mediated by magnetic field, okay? So let's say quite simple process per se. What you have to do if you want to model this is to compute the probability of this conversion, okay? The probability of this conversion, there's no need of going too much into the formulas, but you can compute it. This is probability that the gamma emitted at the source is observed at the Earth by modulation with the oscillation between photon and axion-like particle. This term depends on the strength of the interaction, the magnetic field, the length, and the energy, okay? And finally, what's relevant for us is to remember there is a critical energy here, E critical should be this one, which is related to the mass of the axion-like particle and the magnetic field, okay, of the photon. Why we need the critical energy? Because this tells us where we are sensitive. Let me show it here. If the critical energy, this one, is, so this is computed by the mass and the cross-section here, okay, and the magnetic field. If the mass is something around the nano-electron volt, the magnetic field is around micro-Gauss, and in this range here, what we expect is to have a lot of oscillation between photons. So if the mass of the axion is around the nano-electron volt, micro-electron volt, and the B field is around the micro-Gauss, then the critical energy is around the GV or TV, which means that the oscillation should happen for GV or TV photons. Then the critical energy can be other things, but then we will not see it in the GV, okay? So if it's here, what should we expect at the GV? This would be the probability, the survival probability. So this means that from one photon, we're following this direction. One photon emitted at the source is oscillating into an axion, okay? And this is the probability of this oscillation. And it goes from 0.6 at this energy of the photon, is oscillating, and then it decreases to 0. 0 means zero photon survival probability of the interaction. So by simple this, which you can compute, I will show you later, this is what we would expect for a gamma ray spectrum. So this is energy. This is the spectrum of a source. This source specifically, it's a blazar, PKS 2155, very well-known blazar. And the data, this is Fermi data. The red line is the best fit without the ALP, okay? So the fit, a fit in which there is only astrophysics, okay? If you add, for example, an axion-like particle, let's take the blue line, with a mass, I don't read it very well here, 2 times 10 to the minus 9 nano-electron volt, and a certain cross interaction strength, you will see this oscillating pattern, okay, which is this. It's related to the probability of oscillation into axion during the path, okay? So we want to look at these, they are called wiggles, okay, these irregularities on the spectrum. But you see, even from this, that it's very, very hard to do it because the green bands are the statistical Poissonian uncertainty on the counts, okay? So we want to look at very tiny, tiny effect, okay? But we are doing this carefully, and out of these, we can put limits on the parameter space if we don't observe these wiggles. there is this effect around the critical energy. And there is also a second effect, which is connected to this one, which is what is called recovery of photons toward larger energies like multi-TV. And this is because, I think I never introduced this, but take a minute. I have my source here, and this is, I am observing here. Between me and my source, there is a background light called extragalactic background light, which is in the UV to infrared wavelengths, okay? Now, you remember yesterday, so we have our gamma ray here. This is UV, and the ABL is everywhere. If the gamma ray interact with this ABL, okay, you remember from yesterday, high energy photon plus low energy photons, the interaction most probable is pair production, okay? If you pair produce too much, this means that you lose the gamma ray initially, no? Because if the source is too far away, then you encounter more ABL and you lose the gamma rays. That's why for us, the universe in gamma rays, we cannot go to redshift 10, okay, not even 3, okay, because of this. But what happened? That if instead of this interaction, you have a conversion to, so you have gamma ray, you have the B field here, this become an axion, okay? The axion can crosses larger fraction of the universe because it doesn't interact with EBL, okay? So if you have a photon that become an axion, then enter the Milky Way, there is a magnetic field and becomes a photon again, then you lose less photon, okay, at high energy, and you see this recovery or resurrection of photons, which is very peculiar. There are no astrophysical mechanisms to explain this. So we are looking at both this with, this is more for Cherenkov telescope, and this is, for example, a projection for this is very good with ALP. You see, you expect this only with ABL, and you have this if you introduce the action-like particle with SWIGO, okay? And this is very, very interesting now because we have observed, LASSO has observed one source in which the absorption, this line should have gone here, and instead he saw data there, like the universe was more transparent than it was. There is one source at least, which is a gamma ray burst. I don't know if Elisabetta talked about it, but can only be explained with action-like particle. It's a likely discussion, okay? So it's a hot topic. So at the end, to do this, okay, what you have to do, you take your intrinsic spectrum from a source, from your model, you simply compute, generally speaking, the probability, okay, that a photon emitted at the source is observed at your telescope when you consider action and ABL, okay, depends on some parameter, and this is your observed spectrum, okay. Of course, you have to calculate all the oscillation probability, meaning that you have to compute the equation of transport of action-like particles and photons in the path from the source to us. Luckily, as I told you, you're lucky because finally we have a lot of open share code in which you can use. You don't have to put all the equation yourself again, and you can use something that is done. So let me show you this, for example, why it's good. There is a code called Gamma Alps written by Manuel Mayer, okay? I don't know if you know him, and it's there. You can just install it. Do you know Manuel Mayer? If you don't know, I checked online about Manuel Mayer. I understood it's a very common name. So he is the real Manuel Mayer. It's a very good guy. Not the typical physicist, but so he's one of the most expert in this, and he wrote this code, which is now very much used. It's not the only one, but it's the one that we used, that computes the propagation, okay? You have tutorials there, so you can have mixing in all the magnetic fields, and at the end, it all breaks down in, for example, in Gamma Alps, okay, you have Python scripts, you compute, you make some libraries, You initialize your axion, you define a source with some distances and some position in the sky, and then you say, well, you define the object here, and you add the propagation. You say, okay, well, I have some turbulent magnetic field at my source, and then I have some ABL, and then I add a model of galactic magnetic field, and like that. Of course, you need to know what it's doing, but at the end, by this, you just compute what you want, which is your photon survival probability. Okay, these are different realization of the same. So sometimes you don't need to do to discover hot water again. Yeah. To interact with CMB, the interaction with CMB is maximized not for GeV and TeV photons, but for larger energies. So, okay. So we don't care in function of the energy, you have the CMB peak, and this is the ABL. I don't have a plot here, but with this you need the higher energy photons. Okay, so for example, okay, we take sources that we observe regularly with our telescope, so we don't need even to point the telescope, which are galaxies or cluster or galaxies embedded into the cluster of galaxies. One is NGC 1275, which is the galaxy at the center of the Perseus galaxy cluster. Okay, we have different observation. What do we have to do? Take your source, we have to reconstruct the data. Okay, so these are 3 moments of our source. One is when it was flaring, one is when it was post-flaring, and one is low state. Okay, and we want to look here if these tiny wiggles here are compatible with axions. Okay, so this is delicate because the effect is small, so you have to make a good statistical evaluation. You compare the axion-like particle, no axion-like particle hypothesis, you build a nice likelihood. This is what we want to do. You remember these are very small wiggles, but if you do it carefully, at the end, let me skip this one. At the end, you can exclude by saying, okay, look, I'm not seeing any deviation, so I'm not seeing any significant evidence from the axion-like particle because these oscillations are too small, okay? And as with dark matter, I can say, okay, if the oscillation would have been larger, I would have detected the axion-like particle. So now in the plot, so this is where we are working. I told you, remember, we are sensitive to axion-like particle between 10 to the minus 9 and 10 to the minus 6 electron volt, micro to nano. And this is the cross-section. And we can put, with magic, for example, our exclusion plot here. So we can say an axion-like particle here is excluded by our data. It would have provided wiggles larger than what we can limit. And we were happy because if the limit would have been here, it was nothing new, but then we have this tiny, tiny little thing, places in the parameter space that is excluded by magic. So we could publish it. Okay, so but this is what you do. It's regular, no, in fundamental physics. You take a model, you say, okay, if I don't see it, it's fine. Okay, okay, I can exclude that the axion-like particle is here. Actually, we discovered also that, okay, these are examples of our parameter space. You don't see the mass and cross-section, but you see that here is where we don't exclude the parameter space, and here is where we exclude the parameter space. And you see that, and these are different probability of oscillation from gamma gamma, okay, for this point here. You see that take this one, for example, these wiggles, or this one, we don't actually see it because they are too small. We don't have enough statistics to do so. We can exclude this point here because we have very peculiar features, sudden jumps. So you multiply this to your spectrum, and this is very unlikely to be observed, while these wiggles are actually too small, okay? But still, we can say that we don't have axion-like particle there, okay? So we put our limit, now it's not plotted here. This is the thing that you can expect with CTA, which is much more. Our limit will be something like here. CTA can probe this part, which is unprobed by other instrument, okay? So there are this work, which was made by Manuel Mayer in 2010. And you can think, okay, the big guy are doing everything, but it's not like that, because then I will talk about this. For example, take Francesco Schiavone, who is a PhD in Napoli, and he invented a new method to look for the signature. You're looking at very tiny signature on top of a spectrum. There can be a lot of fantasy there and a lot of ways to do it, even with neural network. And so he's developing, during the PhD, a method to constrain actual particle, which is better than what Manuel Mayer did for CTAO, okay? So don't be shy, and if you have ideas, to think. What I want to tell you is that, okay, we are constraining this part here, but remember, in the big plot, we are working on this tiny area here, okay? So we have, it's very hard to invent an instrument that is sensitive over a very large fraction of the parameter space. If you do, congratulations, then we do our small contribution there. The advantage is that the data are taken by the observatory, okay? So we are just taking data that are used for astrophysics. We take the data and we do our fundamental physics search to see for tiny effect. For SWIGO, the situation is good, actually, because we are looking at this, you remember the second signature, which is the recovery of photons due to the ABL, where it is, there. So what happened? You take a source like this one, another blazar, okay? You remember that it emits from radio to X-ray, okay? We have data from current experiment up to here, and SWIGO is there. Red line, it's a model, so we don't have data there. Now, if we add the action-like particle to the model, we can have the following situation. So these are data points. These are these data points here, okay? And the extrapolation here, the red line, is the one that we would see if there is only ABL absorption, okay? The black solid is the one that we would see if there is the actual particle. So, and this gray area is SWIGO sensitivity. What does it mean? If anything is above, SWIGO sensitivity is detected, okay? Here we don't detect, here we detect, everything above. So in this case, we have a detection of this source with and without the actual particle, because we see these points with SWGO, here and here, okay? Well, here and here. However, take this example here from another source. This is SWIGO sensitivity again. This is the line, if there is only ABL, it's below. We don't see it with SWGO. But this line here is with the ABL, and it's inside the SWIGO sensitivity. So this source, what does it mean? That this source, well, we don't point SWIGO, but we look at the sky, there we would not expect to see anything, but instead we see something, and it can be motivated by axial particle. It's great, okay? So this is what we aim to achieve with the SWGO. Okay, so conclusion for the axial particle, they are valid dark matter candidate. They are called sometimes WISP, weakly interacting slim particle. They leave traces on gamma ray spectrum, so we are looking for those traces, even if small, wiggles or photon recovery, but still they are certainly there. Of course, we have to model well the magnetic field. There are some uncertainties in the modelization, but we have what we have. And there are a lot of open software, so if you're interested, you can develop things and use things that are already done. So this project would have been much more complicated 15 years ago, okay? And they exist for sure, at least to make dishes. Axion exists. Any question to axial particle? Is anybody working on axial particle, actually? Yeah. In which signatures? Which experiment? Ah, in CTA, great. Okay, so with whom are you working? Okay, good. So do you have any comment with respect to what I said? It's all correct? Ah, okay, okay. So you knew which one it was. Okay. Yeah, 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 yeah. Yeah, yeah. It gave the name. Okay. Any other comment or question? Where are you working? In which institute? Here in? Okay. Actually, you can have a very similar effect with Lorentz invariance. Yes, if I have time, I don't know, I will have, there is Lorentz invariance which modifies this probability. So forget about the action. If you have Lorentz invariance, you modify the probability of this interaction at very high energies, and it would have a very, very similar shape. So, but first we see it, and then we fight if it's an action or LIV, okay? But it's very, 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 very similar. I will show you later. You have to know. You have to know, because it's too far away. You really expect, the ABL is well known, you really expect to lose this. Either you have a close by source in the field of view, which is emitting photon there, but it's very, very unlikely. Very, very unlikely. Thank you. No, no, please.
Hello? No, it's good.
Yeah, yeah, it's working.
Okay. So are action like particles enough to explain all of the dark matter density that we see today? No. Okay, that's what I thought.
No, not. Well, there are some parts. I think especially below the, but not the entirety of dark matter. So they can be contributing to dark matter. Okay. Okay, so this is, at the end, it washes out. Just to summarize again, you take, somebody observe the source. You can do it with magic data, if are shared, with CTO forecast, and you just try to see if you are good enough to see tiny effect on a spectrum, okay, to make some nice statistical analysis, and there is space to be more constraining, because if you find new ways to do this, you can put even stronger, stronger limits. The next topic that I want to talk to you about, I'm talking about hot topics that are emerging in the past times, is that of primordial black holes. Now I have an expert. So again, you see now how the number of papers that mention primordial black holes exploded, no, in the past years. One of the reasons, I think you, at least in my opinion, is that these gravitational waves that we discussed yesterday, they were seeing black holes with masses of some tens of solar masses, okay, which are hardly explained by stellar black holes, and they are trying to fill the gap between supermassive and stellar black holes, and primordial black holes, as we will see, could have this kind of mass. So probably is also driven by gravitational waves. Again, in the plot that we were showing now, we are looking at solar masses. Well, there is a wide range here of primordial black holes, and we can see them in TV. Okay, they can be part or the entirety of dark matter, primordial black holes, depending on their mass, as we will discuss later. So, what is the idea? No, stellar black holes are generated by collapse of stars, but in the early universe, primordial black holes can be formed with different mechanisms. Okay, during phase transition, collapse of primordial overdensities while the universe was expanding. So all this mass range of stars, you don't care here, because you are in the early universe, you can have overdensity of hundreds of stars or smaller, okay, according to the moment when the primordial black hole was formed. because we don't know when this happened, we have a mass, a large range of mass from primordial black hole, from tiny, say the Planck scale, to huge, like several hundreds of solar masses, okay? But at the end, you produce them with, this is a subject of study a lot. They can evolve. From once, they can accrete matter, they can merge, they can interact with dark matter. This is studied a lot, from what I know, in the past years. And we know from the 70s that they can even evaporate, okay, by the Hawking mechanism, okay? Now, about the evaporation, this is what we are interested now, okay? There are a few things, and I didn't put too many formulas here, but we know we have a relation between the mass of the black hole and the time, the Hubble time in which it was generated, okay? Which is that simple. So what does it mean? That if a black hole was formed 10 to the minus 23rd second after the Big Bang, it would have now a mass of 10 to the 15 grams, okay? This is 1, 10 to the 15 grams. And this number is useful for what I will tell you later. So there is a relation between the time of production and the mass. There is a relation between the Hawking temperature and the mass of the black hole. The Hawking temperature is, let's say, what you can generate at the surface of the black hole, okay, in terms of quantum physics phenomena in which you have I don't know if you are familiar with the mechanism. I'm not that much, but there you have quantum fluctuation, and the quantum fluctuation can have two lives, one inside the black hole and one outside, and the level of temperature of this quantum fluctuation is related to the mass. So again, you see that if you put 10 to the 15 here, you have energies up to the GeV, 100 MeV or GeV, okay? And finally, the last relation, which is maybe useful for us, is the time to evaporation, okay? So if you have a black hole, primordial black hole of mass 10 to the 15 grams, it will, this is 1, it will evaporate, okay, when the universe is 10 to the 10 years, which is roughly the Hubble time, okay? So at the end of its life, when it evaporates, PB, the primordial black hole, emits all kind of particle as long as the temperature increase toward the end, and it's able to basically dissolve itself. This number, 10 to the 15, it's a generic number, okay, which is telling that if the primordial black hole has a mass of 10 to the 15, the evaporation should be happening now, okay? Not today, but in this period. If primordial black hole is lighter than 10 to the 15 grams, they all evaporated, okay? And if it's larger than 10 to the 15, they will evaporate, but we will be long gone, okay? So for the evaporation, we have this magic number, 10 to the 15. During the evaporation, you have the generation of standard model particle with increasing mass, and as always, you have high energy interaction, and you have your gamma rays, which is what we are looking at. So how this would be observable, for example, by MAGIC or by gamma ray telescope. If you have a burst, okay, the evaporation would appear as a short seconds burst somewhere in the sky, okay? Like there, or there, or there, okay? Now, what is the problem? If it's not happening in the field of view of MAGIC, you don't see it, okay? For SWIGO, instead, SWIGO observes the full sky, so there is a higher chance of detection. So, on the other hand, MAGIC observed several directions in the sky. Who knows? Who can tell that in the field of view, okay, we were observing for 20 hours one source. There could have been a primordial black hole exploding somewhere, and we may have missed it because we were focused on the central target, okay? We have maybe some light during a few seconds there, and our automatic analysis reject that flare, okay? So in IACT still, not continuously we look at the full sky, but we have seen a lot of sky during the time. So there is a search for archival data by Konstantin Frank during his PhD thesis, which, if you are interested in this, actually, is anybody working in primordial black holes? No, except from Claudio. But this would be one of the best work that I read, very, very, very complex, I will tell you why, about looking for primordial black holes in our archival data, okay? And there is one reference among many about SWIGO, okay, that were done by Ruben Lopez and myself some years ago, okay? So we understand we may expect something exploding in the sky. We are interested in gamma rays. We have models for the gamma ray spectrum, so photon energy spectrum, for gamma rays, okay? We have two contributions. One is direct into gamma rays, and one is from fragmentation of other charged particles there, and we expect this spectrum here. Again, another peculiar spectrum, no? Which is not very typical for astrophysical spectrum, with flattening here and a sharp cutoff. It's not important to see now how it's modeled, but this would be the shape, okay, of the spectrum that we may see. And this would be the light curve, okay? The light curve would be, so remaining lifetime, so this is the explosion of the black hole, this is the number of photons, so it's basically absent, until shook, we have a sudden burst. What we don't know, this is a zoom, is the duration of this phase here. It depends on the mass of the black hole, another thing. So we don't know if it will last 1 second, 2 seconds, 4 seconds. We don't know, okay? Which, well, let me skip this, which make the analysis complex, because now, okay, this is, imagine you have your telescope, okay, and your telescope you have events happening center here, the photons, no? The events that you have in your telescope. You have to look for something that is happening somewhere in the field of view that you don't know the duration, okay? So you don't know the position and the duration. When you are looking for something that you don't know where it is, you have to pay attention with statistics, because you can, you have to compute the trials, no? The probability that something happens by chance in your field of view. So this analysis is quite complex, and what was done, I will be quick, is just to look for some clustered event, okay? Because you always have event in the full sky, and you look for some clustering of event in the field of view to be able to say, look, I have an excess somewhere in my field of view, and I'm checking the duration. This is done in this PhD thesis. You have to shuffle the time, not to compute the wrong, the number of trials again. So it's complex, but it was done by him. And this can be done, for example, also for gamma ray burst. Maybe somebody of you is working for gamma ray burst. Why not? Gamma ray burst can happen in the field of view of CTA, and if you want to look for them, you can use the same analysis like this, to looking for clustering of events in time in your camera. So the thesis, I was a review, I read it, it was, I don't know, 150 pages of statistics and 1 page of results, because the results are quite meager. So let me explain this. This is the integration time, so 10 to the minus 3 seconds, 10 to the minus 2, 10 to the minus 1, the duration of the burst that you would expect to be able to see. And this is the limit that you put. So you can put limit, in what limit? I can put a limit, you say I don't observe any burst, okay? And then my limit would be in the number of bursts within a volume in space around me, okay? So the limit here is put in number of bursts per square parsec cube per year, for example. There are limits from several experiments that we heard about, Fermi-Lat, Hess and Veritas. This is Veritas here, okay? Just 2 points and it's not even the strongest. But at least the method to reconstruct is very strong. Better limits, okay, these points should be somewhat here, and this is the limits that we put with SWGO, okay, which are a little better. Why SWGO is better? Because the field of view is large, it's always there, and you can just check now in the full sky, so the angular, the solid angle is much larger, and so the limits are actually one of the strongest in this part here. At the end, this number doesn't tell a lot, but this graph here tells a lot that we are here and we are probing a small, so a parsec around us is very little, no? So these are close by stars, and we can detect only very black holes that are happening in proximities to us. Okay, so it's not, if dark matter is hard to find, actually particle, I don't know, but this is, the nature should be very, very gentle with us to place a primordial black hole of the right mass very close to us. But, I mean, I don't know. It could be many, okay? So about now the mass of the black hole, and I'm about to finish. Mass of the black hole, grams. We are sensitive here, 10 to the 15, okay? And there is an exclusion by, well, actually more like here. These are excluded by Fermi-Lat because of all the primordial black holes that have already exploded, evaporated. They would have left all these diffuse gamma rays in the sky. We don't see them, they are excluded. There are a bunch of limits, I'm not that familiar, up to 10 to the 55 grams, so very large masses, which exclude a lot. And this number here is the question that you asked. This is the fraction of dark matter that could be in black hole, okay, which is interesting. So 1 means all the dark matter is in primordial black holes, okay? Here, for example, I'm saying, okay, only maximum 1% of dark matter is in the form of black hole, and so on. And you see there is a window here, which is unproven by limits there, which is what is called now asteroid mass size. This mass here is the mass of an asteroid. 10 to the 15 gram is not that much. 10 to the 18, roughly, is the mass of an asteroid. So there could be, unproven, primordial black hole of that mass that could be actually the entirety of dark matter, okay? Now, it's hard to look for this directly from this signature, from this one, because the energy is wrong for IACTs. I'm not sure for integral. But you know, this is standard scenario, no? For example, we said that all black holes must have the same mass. Well, this scenario is the first one that you think about, but they can accrete, they can merge, so there could be primordial black holes of different masses. So we don't know exactly, this is a hot topic. So, but still, they could contribute to the entirety of dark matter, okay? This search, what I want to tell you again, this search is fine because you don't have to point, you just use the data, you make a nice, clever analysis, complicated one, and you put your limit. So, conclusion for this part, TV gamma rays can be seen when PBH evaporates, okay, around this mass here in the naive scenario. We can have serendipitous events in our field of view, which for me, for CTAO, is one of the hottest topics, to look for anything happening in the field of view. There are models, but of course we don't cover the scenario completely. And there are pipelines that you can use and develop, okay? The results are modest, the expectation, but it's worth having a look in our data, okay? Any question to primordial black holes? Yes. Faccio io.
Can you go back one slide? Okay, so you said that you have to look into archive data that you made. So you are always looking only for the burst. But can
Yes.
you say, because the PBH is evaporating throughout its entire life, can you tell if it's different from another astrophysical source somehow?
No, but if you, before the final burst, the level of photons is basically 0. So you can only see it, okay, in the final phase. So you don't have signature here except from gravitational signature, okay? At least to my knowledge. So you can only have the chance to see this part here. So with gamma rays, no way.
And can you go back to the sensitivity? So, no, one more, yeah. So why is it like a parabola? Because it looks like after 1 second you start to lose sensitivity. Is that because the photons become too high energy or because the flux is too small?
Okay, so the maximum sensitivity is for 1 second. It's a good question. The fact that it's worse with 100 seconds, I don't remember why it's worse. I think you have the same amount of photons. Yes, it's because of that. You have the same amount of photons, but diluted in 100 seconds, okay? So your statistical significance is worse than if you have the same amount of photons in 1 second.
Okay.
You know what I mean? We are looking at, it's always the same. We have background event, okay? And with uncertainty, and we are looking at an excess of event, okay? Now, if this is my excess, suppose that is 100 event, in a large time window is small, okay? But the same number of excess in a small time window is large. So this is very significant, and then my limit goes down. This is little significance, and then my limit goes up.
But why does it goes up after 1 second then?
Here,
Yes.
this is, okay, so this we explained. Well, here is almost flat, and this shape here, this shape for SWJO is too short, okay? Now it's too short,
Okay.
okay? So you haven't collected enough background and signal to see it.
Just one more
Yeah,
question.
please.
Why can Fermat probe 10 to the 8 seconds? This is not a burst anymore, right?
Because Fermi doesn't have sensitivity at 100 GeV, the temperature there is related to the mass of the primordial black hole, so Fermi is super sensitive. But only to MEV photons, which comes from primordial black holes that have already evaporated. Okay?
But the type of analysis is similar?
No, because there you don't have evaporation. They are already evaporated. So the Fermi analysis is simply the following. I look at the sky, I check all photons in the diffuse, not the point-like photons, okay? Because all these primordial black holes have evaporated. They have injected MEV photons around. What I see now is a diffuse sky with MEV. So I check for diffuse signature in MEV, GV, okay? And then I have to say, okay, because I see them, I see diffusion, but then I have to say, okay, I expect that many from Blazar, that many from other astrophysical sources, and there is no space left for primordial black hole, okay? So they can explain all the diffuse MEV background with astrophysics, okay? That's why the limit is so strong.
Okay, thank you.
Any other curiosity? Please.
Just to see if I understood, so you said the magic number is like 10 to the 15 for us to see now?
For primordial black holes to be evaporating now.
Now, yes. And we only see like the last seconds of the lifetime, right? So are those sensitivity curves any use for us?
No, these ones, yeah. No. We are not sensitive in this area here.
Oh, okay.
It's just to tell you that yeah, we will be sensitive in this,
Yeah.
roughly this part here.
So maybe in the future, in the long future.
I think not really long. The issue will be that we said now the magic number is 10 to the minus 15, but there are a lot of studies, and I'm sure the theoretical physicists have a lot of fantasy that they will say, no, 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 no. If I assume this, then the mass will be 10 to the 20, and then we can observe 10 to the 20 with magic, and then we will do another study, and like that. No, because we don't know. It's really, there are clustering of primordial black holes, there are interaction. We are studying things that are not mapped completely, so it's fantasy, but it's also good work, okay? So everything is true except, so you take this magic number 10 to the 15, but it can be another number, okay? So it's still valid, in my opinion. I mean, dark matter is there, as we don't see it somewhere, it should be explained, okay? So we have to look for all possibilities because the missing mass is there.
So let me see if I understand. So this mass of 10 to the 15 grams refers to the mass of the black hole when it's formed at the early universe, right?
Yes.
Yeah. So assuming that it gets
Exactly.
formed at the very early universe.
Exactly.
Because if a black hole is evaporating, say, within the next 10 years,
Exactly.
the mass is, of today is much smaller, of course, right? For a black hole to evaporate in the next 5 years,
yes,
the
but
mass is tiny.
yes.
Well, tiny.
Well, yes, but
10 to the
you have
10 to the
accretion,
5.
you have interaction. So it's a reference mass, in my opinion.
Okay, so you said that Fermat constrains at the PBH evaporating photons with MEV energies, right?
Yeah.
So there's no way to skip the MEV energy range, right? So if Fermat already constrain PBHs that are evaporating in MEV photons, why would we
Not
expect...
that are evaporating, that have evaporated.
Yeah, but if there are PBHs evaporate now at the MEV range, they should have seen also, right? What I'm saying is that they would always find that before, no?
Yeah, okay, understood. I'm not sure that Fermi has developed a pipeline for this burst in the sky, short duration event. I don't think so.
Yeah.
So it's a good, this could be a really hot topic.
Yeah, it's just because I feel like the limits look like they are not connected. But I feel like if Fermat did not find an excess of MEV, a PBH that is evaporating today and it's evaporating TV photons, they should have evaporating MEV before, right?
Well, yeah, again, it depends on the mass, no? So
Yes.
you should see evaporation depending on that. And we don't know what the mass is like to be now. But this about Fermi, it's an interesting work. I never saw anything about looking for sudden flux variation in Fermi.
Okay.
And it's good for this and other topics. Okay. Okay, so I will have time just to show you probably one last topic, but I like that I reached here because it's my favorite one. Yes. I'll tell you why later. So, well, it started, well, I knew about this because there was some studies. Once I was asked to make a review, all this history started because Manel Martinez asked me to make a review of all the fundamental physics topics at ICTs when I was a PhD, and so I had to study and find all the literature. And I discovered something about magnetic monopoles, and I knew a few facts, but then 2 years ago in Padova, I read a seminar in Padova, organized by the theorist, by Takeshi Kobayashi, which is a name for me that is, I have imagined Takeshi Kobayashi came in and, I don't know, he made a lecture on the whiteboard, no slides, and then we started to discuss because he's a theorist, really working in magnetic monopoles, and he didn't know anything about experiment looking for magnetic monopoles, okay? Not that much, okay? So we started to collaborate, and then Daniele Perri was his PhD. And we have 2 works about it. So this is, okay, it's more interesting when they were talking about that in the 70s, and you see that now it's kind of stable. But I hope that after our paper, no, I'm joking. So what is the problem? Magnetic monopole. You know, no, that Zwicky, if you give a magnetic bar to him, and he will break it in 2, you will still have the two poles, no? Because this is what we know so far. We cannot generate magnetic monopoles now. However, if there was magnetic monopoles, this would be great, because the Maxwell equations would become symmetric, and we like symmetries, we like elegance, so this would be great. I mean, that they would exist. It's strange to explain why it's not like that. So we start. The first description of a magnetic monopole is by Paul Dirac. We could have invited him at lunch, but he was even pickier than Zwicky as a character, so we don't. And he was trying to find a way, okay, to solve all these, and especially to symmetrize the Maxwell equation, and also to explain the quantization of the electric charge. And it appears that if you invent a magnetic monopole, you can fix this, okay? Now, the first idea was a very fancy one with a semi-infinite string solenoid, semi-infinite, so that you have the magnetic charge only once. This is microscopic, so you don't see it. And at the end, but the original idea was good, because he found a simple relation between the electric charge and the magnetic charge, okay, which is, by this theory, by this model, which depends on an integer number. So you have the Dirac charge, which is 1, but you can have n times the Dirac charge as a unit of magnetic charge. And the magnetic charge and the electric charge, are quantized, and they are connected one another. And because it was quantizing the charge and fixing the Maxwell equation, Dirac himself said one would be surprised if nature has not made use of magnetic monopole. Then, as it always happened, okay, so this was 20 years before, but the theorists, no, they said, okay, we go before the CMB, no, and because the time before the cosmic microwave background cannot be seen, but can only be inferred by particle physics, they can invent whatever they want, because they make prediction out of it, but you have so much energy that you can add your fantasy, you can add your new symmetries, and it can be there, okay? So they found that the magnetic monopole is very generic, okay? And you can found it when you have phase transition in the universe, okay? And there you have object. Now, I'm not a theorist, so pardon me, but maybe somebody can explain it better. But you can have this topological defect. Means that you have regions which are of the space separated, and what's inside doesn't have the possibility to interact with the other part anymore, and maintains the condition of the universe back then. Okay, let's skip about this. What we need to learn is that depending, like primordial black holes, depending on when the phase transition happened, the magnetic monopole mass can be either very, very large, or so during grand unification theories, but then there are intermediate mass theories in which the magnetic monopole is 10 to the 6, okay, GeV. These are very large masses anyhow, so accelerator are out of business, no? The definition is zero-dimensional solid tonic solution of the vacuum manifold. Okay, this is too much for me. But I'll show you the next slide, and I think it's a picture of a magnetic monopole. I think it gets me a little bit the idea. So this is from Patrizzi from Italy. This is a very nice review there. And you see that the magnetic monopole, it's a soliton in the sense that what's inside cannot really interact with our current world now. Is blocked kind of in time, but it contains all the fields that were present in the early universe, okay? So grand unification bosons, electroweak unification boson, etc. And it's an extended object, okay? It's not a point-like particle, if you want. Now, there are two classes. This is the good, in which you have grand unification bosons there. So moments when the universe was different than now, or intermediate mass in which you don't have this scale of boson. But you imagine you have this agglomerate of particle blocked in space, okay? And inside here, you have the condition of the universe back then. And they have a magnetic charge. This is important. They have magnetic charge 1 or -1. Say, okay, they are fancy, okay, but because they have magnetic charge, they have a strong effect of the in the universe. So there are two indigestion that you can do with magnetic monopole. One is cosmological, okay? So suppose you have this phase transition in the universe, you produce them during this phase transition, and then you can compute the abundance, okay? And it happens that the abundance of produced monopoles can easily over-dominate the energy density of the universe. If you produce too many of them, they are blocked, they have a mass, and they have too much energy. We don't see it. Actually, inflation was started to explain the fact, to explain that, okay, we produce a lot of them, but then we stretch the space, and the density is now smaller than what it was at the beginning, okay? So this was one of the motivation for the theory of inflation. So this is just by abundance. But there is another reasoning, which is if you have too many magnetic monopole, so they have a magnetic charge. If they encounter a magnetic field, okay, if there is a magnetic field like this, for example, in our galaxy, and you have a magnetic monopole, it's like the electric force. It would be accelerated linearly into the magnetic field, okay? Like an electric charge is linearly accelerated into an electric field. The same thing. If you accelerate the magnetic monopole, you extract energy from the magnetic field, okay? So in order to maintain the galactic magnetic field at the level of that we see now, which is micro-gauss, you have to say there were not too many magnetic monopoles, otherwise this magnetic monopole would have drawn all the energy from the magnetic field of the galaxy, okay? And this is one of the basic limits called Parker bound. I will come back to that later. Okay, fine. So we have a theory, we have some constraint, and now you say, okay, but how can I see the magnetic monopole, okay? At the end, okay, nature is complex, but experiments sometimes are easier. You have a moving magnetic charge, okay? It induces an electric field, okay? So it's like, if it's moving in your detector, it's like a strong electric field happening in your detector. So there are people that study this, and at the end of the day, the search for magnetic monopole is kind of the search for a charged particle, okay, that has the same mechanism that any charged particle, but deposit a lot of energy in your detector. So you have elastic collision, energy level crossing. For relativistic magnetic monopole, you can ionize, and you can have pair production, okay? The usual thing about particle, charged particle interaction, okay? You can also have Cherenkov light, because you have a charged particle moving into the medium, and we know it emits Cherenkov light. Now, which is the interest for us? The Cherenkov photon yield of a magnetic monopole depends on the charge of the magnetic monopole, and at the end, for a Dirac magnetic monopole, would be 4,700 times that of a muon, okay? So, a muon makes some, or an electron makes some light in the atmosphere. A magnetic monopole would make 5,000 times more light in the atmosphere. Okay? And they can do fluorescence, Cherenkov, etc. So at the end, for me, that I'm a simple-minded experiment, a magnetic monopole is like a supermuon, okay? Crossing my instrument, or super electron. How can we see this? Okay, there are direct detection experiments. This one called Macro was in Gran Sasso, in which you actually want to see the energy released by the magnetic monopole in the detector. I don't have time to go too much into the detail of this detector. And this is I just put you because it's the strongest constraint there. But let me go to IceCube and us. IceCube, I don't know if you know IceCube, it's a detector in the South Pole, which normally sees you have a neutrino, which can convert into a lepton. Lepton is charged and emit Cherenkov light in the ice, and you see it with the detector, okay? So you see the lepton. Now, I told you the magnetic monopole is like a super lepton, okay? So they expect to see a super boosted, super strong light in their detector that cannot be explained by the energy of a standard lepton, okay? So they're looking into this, and they put limits that I will report. The same thing can be done here in South America, in Argentina, with Auger, because there is, Auger is looking at shower in this direction from cosmic rays, but there is fluorescence light, okay? Now, again, you have, instead of a proton or whatever, you have a super particle emitting so much fluorescence light that you cannot explain it, no? With your standard mechanism. And so, Auger is doing a lot of searches for was doing a lot of searches for magnetic monopoles. But for us, it's the same, for both Swigo and us. If we have, you remember this plot, if we have a magnetic monopole, simply, this is very similar, but the amount of light is 5,000 times more. We should see a flash, okay? So the fancy thing about this is that everything was started by a master student of Ulrich Schwanke, which is still around, called Gerrit Spengler, which in a diploma thesis made all these studies about magnetic monopoles, and this is where I started to review this topic. So you find this only and an ICRC proceeding. And he studied 5 years of data corresponding to 3,000 hours of Hess data. It was never published by Hess, okay? And looking for signature of magnetic monopole. Now, I'll show you what is nice about this. You have, so we know that the Cherenkov angle, okay, depends on the speed of the particle, okay? So here, so a particle with 10 to the 5, Lorentz factor emits very large and 10 to the 2 very narrow here. And this is a little complex. But at the end, let me just show you like this. This is our telescope, and this is a track of a particle hitting the atmosphere. What did we learn yesterday? That if something happens here, the shower dies at a certain height, no? It dies off. And then you have only this part here of the light. But the magnetic monopole makes Cherenkov light and doesn't really crosses the Earth, so it doesn't interact. It emits Cherenkov light throughout the entire path from the top of the atmosphere to the ground, something that cosmic rays doesn't do. And this, because the index of refraction of the atmosphere changes, means that you have light at the beginning here, so this Cherenkov light is reflected inside. Then, when it's below, you see the Cherenkov angle increase, and this light goes outside. But then, when it's even lower, the Cherenkov angle increases, but now it's focused back in the camera, okay? So you see something that you don't see with cosmic rays, just by geometry. So you can see twice the signal, one from very large altitude, like 40, 50 kilometers, and one from very low altitude. This means that in your camera of the event, you would see, these are simulations from Gerrit, you see double spots, okay? double spots like that. Double spots, there are, in some cases, if you have iron nuclei, but this is very fancy. You don't see it with cosmic rays. And they are very bright because there is a lot of light and very strange, okay? So this, what is nice about this, that these, if you make a standard analysis, these events are thrown out. You don't this consider as background, no? And so there is no confusion with gamma rays.
From the experimental point of view, this is extremely hard because this is the kind of thing that you cannot clean very easily the image for, because it's maybe you have a pixel with an excess of light and you are looking for a few pixels with an excess of light. Wouldn't it be simpler to look for super bright muon rings? Wouldn't it create something
also,
like that?
There are, there are. This is one geometry, you can have rings also there. But whenever you have, and not all the time you have double images, but whenever you have very compact, even saturated pixel, but you can saturate pixel in one camera, but you cannot saturate pixel in more cameras with some geometry, okay? So it's very easy, exactly. With one telescope, you're right, but with more telescopes, it's a geometrical factor here, which is super clear signature. It shouldn't be complex. The problem with CTA is that this will be thrown out immediately.
In any case, for the stereoscopy, I mean, would the lower altitude signal be seen by several telescopes as well? Because then you are very close to the reflector
yes,
already.
Yes, few telescopes, yes.
Yes.
But even with one, so there is, and actually all the geometry was studied by Hess in a simplistic way. This was not done, as I will argue, for CTA. It's a good PhD work to redo it. Okay, so he made searches on archival data, okay? And at the end, if we put all the limits together, we have experimental limits. We are plotting limits like this. So ice cube, I told you about here. It goes gamma beta, so Lorentz factor roughly 1, okay? Auger is here, very, very ultra-relativistic to give enough fluorescence light here. Macro is here, and Hess is right above there, okay? So this is the Lorentz factor of the magnetic monopole. These are the flux limit. Now, what we did, and so this is gamma beta, is to use something that is yeah, I told you about the Parker bound. Let me skip this one. Let's go back to the acceleration. So we have a magnetic monopole is linearly accelerated into a magnetic field. There is a back reaction I told you about. The accelerated monopole extracts energy from the cosmic magnetic field. The monopole bounds are then affected by the acceleration, actual acceleration that is happening in the universe, okay? So at the end, if you have a model from cosmic magnetic fields, you can compute a model from the acceleration, from the cosmic magnetic fields, you can compute the acceleration and in function of the mass. And this was motivated because, okay, let me skip this one about how you compute the acceleration, because with gamma rays telescope, something that I didn't report, we are doing something very, very interesting, which is measuring the intergalactic magnetic fields. We talk, during the Axions, we talk about intergalactic magnetic field, okay? You have your source, you have your telescope here, and you have the intergalactic magnetic field where there is, well, the region where there is also the ABL. The intergalactic magnetic field is, I said, below nanogauss. It's interesting because do we have magnetic fields in between the targets? We don't know because it can be of primordial origin or not. So far we have only upper limits, about 10 to the minus 9 nanogauss by CMB anisotropies. But now with gamma rays, with our telescope, we are putting lower limit. Lower limit means that for sure we can say that the intergalactic magnetic field cannot be smaller than 10 to the minus 16. Why is like that? This should be another talk. But this can be done with gamma ray telescope. And it's one of the few, I like it because it's one of the few actually physical measurement that gamma ray telescope do. So this part here is allowed by the intergalactic magnetic field. So if I tell you that there is an intergalactic magnetic field, it accelerates the magnetic monopoles, okay? And so this is, we checked all the possibilities here, and we reported this. These are new. Let me just skip this, otherwise it's too much. At the end, if you have a model of the magnetic field, like here, you can connect the velocity of, because you have the acceleration, but the acceleration depends on the mass of the monopole. So you can connect the speed now of the magnetic monopole to its mass. The speed is not a physical parameter if you want, but the mass of the magnetic monopole is a very physical parameter. So if you have this model, and now we have this model, you can connect the velocity of the monopole to its mass by this function here, okay? Because you know how it was accelerated from early times to now. It's not that complicated. And at the end, we probe this region of the parameter space. Sorry, I have too many slides, but I want to conclude. And so we pass from limits, this plot I showed you already, in function of the speed, to limit in function of, where is it? Here, in function of the mass, okay? So the same plot now say, okay, we have the galactic Parker bounds, we have the macro one, but we know that ice cube is sensitive to monopoles that heavy, Auger to monopole that light, and here is where CTAO may be in a region where maybe ice cube and Auger are not sensitive, okay? They are weak, but they are not excluded. And for us, it would be, and for SWIGO will be much better because of the larger field of view, but nobody has made any simulation about it, okay? But why not? As Dirac said, they are too nice not to exist, the magnetic monopole. Now we have a framework to connect mass and speed considering the IGMF where they accelerated. Okay, so I want to skip the LIV. I want to go to the conclusion of all of what we said today. Okay, the lunch is ready, and let's ask Zwicky, what would he say about what we have discussed today? Well, first of all, we can go buy some actual dark matter. There are songs, wine made in California called the dark matter. I never tried it. We have promising recipes, in my opinion, because we have a lot of laboratories, especially in the universe, distance, age, energy, B field, stable and varying sources. We have a lot of messengers and things happening out there. Thanks to theoretical physicists, we have a lot of theories, and many times we have gamma rays involved whenever we have high energy particle, okay? So we can pick our guide to look for things. Okay, however, if we put results on the table, we have not yet found new physics, and I think it's fair to assume that new physics, it's hard to find. It can be behind the corner, can be years away. What is nice for us is that many of the things that we said can be found in the leftovers. We don't need to point the telescope. We don't need to. We just need to make clever analysis, okay, nice analysis, and we may find small hints of things in the new physics there. And even with null results, we constrain the space, okay? And history showed that this is, the serendipity is something that we may expect, okay? This is important to model for CTAO and to think about these pipelines before the instrument comes. But at the end, okay, even the last message, no? Well, there is also dark matter RAM. Where do you look for beyond standard model? No, this is the original word was where. This is where you look for your lost keys, okay? Where is more probable? Behind the street light, okay? Because if it's lost in the dark, you have lost them. we have to work on where the theory goes and where it's more probable that we have a limit there. So this is where we are doing beyond the standard model physics. And I think I really stressed you too much, so thank you very much for listening.
So more questions before we go for lunch.
It's late.
Thank you for the talk. I just would like to understand one thing. You said that the magnetic monopoles would emit Cherenkov light since the beginning of the atmosphere.
And until the ground.
Until the ground, right? So can we not like mount a Cherenkov, like atmospheric Cherenkov telescope in higher altitudes to eliminate the Cherenkov light produced by cosmic rays and get just the magnetic monopole
there's no
part?
need. There's no need because it's the shape of the image is and the intensity is that large that there is no confusion. All the results that I reported are 0 plus or minus 0. Is that different from your standard event that there is no confusion. So you don't have to go elsewhere. You just have to make the analysis to look for that fancy signal, okay? And you count 0, okay?
Okay. Thank you.
And nobody did that for SWGO or CTA.
More questions?
No, it's a comment and a question. The comment is for everybody that Rafael is going to give a lecture on IGMF, intergalactic magnetic field. So this, I guess, will be useful.
Good. I didn't know.
And the question is, so when are you going to offer a master thesis on magnetic monopoles, Claudio, for SWGO? I think you are the right person to propose the topic.
Any other question?
Thank you for talking.
Thank you.
It's possible to see or to source for some evidence of dark matter and gamma ray emission comes from a small source like pulsars or something.
Pulsars. For sure, the axions, pulsar have large magnetic fields. So the action mechanism, photon, magnetic field, axion, is observable in pulsar. I'm not that familiar. What I know is that the signature is in the MeV range, not in the TeV range, considering everything. So the limits, there are strong limits, but they come from Fermi, so smaller energy than us. So pulsar, yes. But the other thing, WIMPs, no, because it's too small mass, and all the rest that we talk about, no. But for axion, yes, and a lot. So if you study pulsar, you can find axions there.
Any other question? Well, I guess not. So thank you, Michele.
Thank you.